symposium to commemorate the birth centenary of Chandrasekhar. Now, what I will do in this talk is to first give you a flavor of the AstroSat instruments during first 15 or 20 minutes, and then next 30 minutes I will explain to you what kind of science you can expect from AstroSat by giving example of different kind of astronomical objects. Particularly my emphasis will be on X-ray emitting sources, and although it carries very sensitive ultraviolet imaging telescope, I will be only briefly touching on that aspect in this talk. Now, AstroSat is a broad spectral band Indian astronomy satellite. It will be the first Indian mission fully dedicated to astronomy, and the emphasis of this will be on multi-wavelength observation and also broad spectral capability. Now, it will be a truly national space observatory, because it will be open not only to the persons who are building the instruments, but also to every observer in India who wants to make observation with AstroSat, and to a limited extent from second year onwards will be open also to international community. Now, AstroSat, as you can see, involves almost all the leading astronomical institutes in India, led by TIFR. So, the instruments are being developed, 3 of the X-ray instruments are being made at Mumbai at TIFR. ISRO Satellite Center is making the X-ray sky monitor at Bangalore. IIA and IUCAA are jointly developing ultraviolet imaging telescope. I will tell you about details later. And Raman Research Institute involved with TIFR in large area X-ray proportional counter experiment. We also have 2 international partners, Canadian Space Agency and Leicester University, who are providing some of the vital parts of the instrument which we require. Canadian Space Agency is contributing the photon counting detector for the ultraviolet imaging telescopes, and Leicester University is providing us the CCD and its front end. Now, why AstroSat? It is a natural question to ask. After all, we have so many half a dozen X-ray satellites working right now: Chandra, XM Newton, Integral, Swift, and so on. So, why AstroSat? Now, if you look at all these missions, you will notice one thing, that these missions are, take for example Chandra. It is a fabulous mission, has fantastic angular resolution and very high spectral resolution, but Chandra and XM Newton both are based on reflecting X-ray reflecting optics, and therefore their response is limited to 0.1 kV to 10 kV essentially. So, there is no, now in the case of XM Newton, there is also ultraviolet monitor, optical monitor, which is also sensitive ultraviolet, but it has limited capability. The reason is a 30 centimeter telescope, and it can essentially do photometry. That is why, even though it it has been working, results have been not as extensive as done in the X-ray band. Integral is a observatory which is made mainly for hard X-ray astronomy, and detectors, cadmium telluride detectors used there are sensitive from 15 keV to 100 keV, but there is also low energy detector, but unfortunately it is not working very satisfactorily. Therefore, you will find that from Integral most of the results which you get are above in hard X-ray band only, and in fact there is a gap between 2 to 15 keV. And the optical monitor is a 2-inch thing, 2-inch camera which has very limited sensitivity. In the case of Swift, Swift is the one mission which comes very close to AstroSat in terms of its spectral coverage. Swift carries a CZT instrument of very large area. It also has optical monitor similar to the one flown on XM Newton, and it has a X-ray reflecting telescope of about 200 centimeter square area, which helps in localizing the, once you detect a gamma ray burst or X-ray transient, you can point the telescope and localize it and then do detailed studies. But the Swift also has a gap, that there is no instrument which covers 2 kV to 15 or 17 kV, where the CZT detector takes over, and therefore, you can see that from Swift timing results have been very few. So, AstroSat will fulfill this, will fill this gap. It will have multi-wavelength observation capability with 4 co-aligned instruments, which will cover visible, near ultraviolet, far ultraviolet, soft X and hard X-ray bands. It will have very broad spectral capability in X-rays, right from 0.5 kV to 100 kV with 3 instruments. large collecting area, you can see that it is very comparable or even more than the collecting area of highly successful PCA array on RXT mission. PCA of course has been working for last 15 years and has produced excellent science and in fact discovered all kinds of new phenomena including kilohertz oscillation and so on. So, so these detectors will be more sensitive than the one on the RXT, and in hard X-ray about 20 keV will have the largest collecting area flown so far in any mission. It should be about 5,000 centimeters square. Why is it so? I will tell you the reason. Then there are twin telescope, UV twin telescope UV instrument, which is 38 centimeter primary, two telescopes, each with 38 centimeter aperture mirror. One is will be sensitive near UV and visible, another in the far UV, and there are photon counting detectors which have been provided by Canadian Space Agency. Now this telescope has excellent angular resolution, 2 arcsecond, which is far better than any mission flown so far. In fact, the Galaxy, which is very highly successful UV mission, has angular resolution more like 5 to 6 arcsecond. So this 2 arcsecond resolution will enable one to look deeper into the UV sky. Then there is a scanning sky monitor, very similar to one flown on RXT, which will do the study of transients and variable sources. And then we have a very high time resolution, that is each and every photon detected by LEXPC will be time take to 10 microsecond accuracy, and therefore you will be able to do very good timing analysis, and it can handle counting rates up to 40,000 counts per second. So what are the associated instruments? There are first is the large area X-ray proportional counter. This is there are 3 identical detectors, each with an effective area which will range between 2000 to 2400 centimeters square, which will be sensitive in 3 to 80 keV band. It is a 50 micron thick Mylar window, therefore you can go down to 3 keV, and it will do low resolution study of continuum spectra of X-ray sources, because proportional counters have inherent limitation in the energy resolution. Then we have CZT imager, which is similar to what has been flown on the Swift, but its area will be modest, about 500 centimeters square effective area. Geometrical area is double of that. The advantage of CZT is that one will be able to operate almost near room temperature at -10 degree or 0 degree and improve the energy resolution by factor of 2. So this will be very well suited for study of cyclotron lines in the spectra of pulsars. Then we have the soft X-ray imaging telescope, which is very similar to XRT flown on Swift. Area is also very similar, and we are using conical foil mirrors for this purpose, which have been developed at TFR, and it will be using X-ray CCD at the focal plane to do medium resolution X-ray spectroscopy of all kinds of objects. Its effective area will be about 200 centimeters square 1 keV, and it drops to about 25 centimeters square 8 keV. Now why this instrument? Because this instrument enables one to extend the energy range right up to 0.3 keV, whereas the LEXPC has limitation of 3 keV. Therefore you can see the study the absorption in the interstellar medium or near the sources and so on. Then we have the scanning sky monitor, which is, as I said, very similar to what has been flown by the MIT group on the RXT. Area is also very similar. So essentially these are position sensitive proportional counter, which have coded mask aperture, one dimensional coded mask aperture. You can localize the position of transient once you detect it to an accuracy of 3 to 6 arc minute, depending upon the brightness of the source. And then UVIT has, as I already told you, 2 similar telescopes with photon counting detector, and finally a charged particle monitor to control the operation of the instrument in zones of high background radiation like the SA zone. So how does this is how the LEXPC looks like. It is about 1.2 meter long, about 50 centimeter and 15 centimeter deep. Why we get high effective area, large effective area with LEXPC? Because LEXPC, unlike PCA, is a deep detector. It's 15 centimeter deep. So this is achieved by having 5 layers of X-ray detecting, X-ray detecting anode layers, and therefore, this is because of the large depth of 15 centimeter, the cross section for detection of high energy photon is much larger, and therefore, we will be having a much larger effective area compared to RXT. As usual, there is a veto layer all around to reject cosmic ray produced background and also component interaction of high energy photons. And this is the XA-CCD camera, XA-CCD mounted in thermoelectric cooler. It is a 3-stage thermoelectric cooler. The CCD needs to operate at minus 80 degree centigrade temperature. So, this is achieved by using this cooler, and then it is coupled to a cold finger, which in turn is attached to a plate, which is a large area plate, which cools it down further and achieves a temperature of minus 80 degree. Now, this is how LEX PC when fully assembled looks like. This is the detector part, this is the front end electronics, and the high voltage and command control units are all mounted at the back of the detector, and this is the collimator section. It is a 1 degree by 1 degree field of view, and collimator is made in a very novel manner. I do not have time to go into detail, from a 5-layer material of tin, copper, aluminum, which provides sufficient rigidity and strength, 120 to 50 micron thick material. And this is now we have already fabricated all the parts of the 3 LEX PC unit, and this is one of the engineering unit which is undergoing thermoic test at Mumbai at TFR, and hopefully next 1 week it will complete this test. Now, the SXT is as I told you, it is based on the use of conical foil mirrors, similar to what has been used in highly successful earlier missions like ASCA and now in Suzaku, and these are arranged like paraboloid, section of paraboloid, hyperboloid, and then you have a CCD detector, the focal plane. Now, CCD detector differ from the optical detectors in the sense that they require large depletion depth to detect X-rays of up to about 7 or 8 keV. Therefore, they are not commercially available. You have to specially make them, and if you were to procure from a company and order it, it will cost us several $1 million. So, we learned about that Leicester University, which made the CCD detector for Swift XRT. They had a spare CCD. So, we approached them, and they are saying that they will be very happy to collaborate, and that is how this collaboration is emerged. And so, see all the parts of the this is the tube made from CFRP, and there is a thermal collimator on top of that, and there is a deployable cover. You will keep it closed till all the outgassing is over, and then give command to open the cover. Similarly, door of the CCD, camera is kept closed at the time of launch, and later on it is deployed. And there are reductive sources by which you can calibrate these CCDs during the flight. Okay, then CZT imager is a CZT detector arranged in 4 quadrant, 1024 centimeter square effect area. It is a 2-dimensional coded mask aperture, similar to what is there on the Swift, and it is a radiating plate which cools it to about minus 10 degree temperature. And this is the twin telescope UVIT instrument. You can see the primary mirror is here, there is a secondary, and then you have the not pre-collimator, shield which prevents the stray light from entering the telescopes, and then at the focal plane you have a filter wheel, and then you have the CCD detector. And in the case of the one telescope which will monitor the optical and near UV, there is a dichroic mirror which will split the beam into visible and the near UV part, and then 2 separate detectors will count the intensity and find the position. So, here is the specification of the UVIT instrument. You can see that one channel will cover, it is a field of view of 0.5 degree. Although the optics itself is designed for 1 arcsecond resolution, but when you fold all other effects, then it becomes 1.8 arcsecond, close to 2 arcsecond. So, this is the far UV 120 to 180 nanometer. Optical channel will also be used for improving the aspect determination and also for controlling the spacecraft. So, there is a channel plate multiplier based detector system which requires 8000 volt high voltage unit that is to be procured, and then once you get the photon, they get converted into, it releases photoelectron, multiplies through channel plate multiplier, incidence and the photocathode gets converted to photons, and then photons are led through a fiber optic bundle to a CMOS detector. So, that is how this works. So, this has been provided from Canadian Space Agency. In fact, TFR group and IUCAA have been deeply involved in the characterization of this and calibration of this instrument. This has now been fully qualified both through shock, vibration, thermowake and so on, and is ready for use. So, this is what I was saying, that LEX-PC is a very large area. Here for comparison I have shown the area is a function of energy for RXT PCA. You can see RXT is excellent below 20 keV. That is why most of the RXT result have come actually, if you see the RXT papers, there are 1500 of them, they all come below 20 keV. The results are based on 20 keV observation. But as you go to higher energy, the RXT efficiency drops very rapidly for the simple reason that RXT is only 3 centimeter deep versus 15 centimeter for the LEX-PC. So, the ASTROSAT, this is the curve for ASTROSAT, and ASTROSAT detectors will be filled with xenon at a pressure of 2 times that of the LEX-PC RXT, and therefore, that will be further advantage. Okay, this is how the ASTROSAT satellite will look like. This is the top deck on which all the detectors are mounted. Red boxes are the LEX-PC units. The two tubes which you see here are the twin UVIT telescopes, which again have deployable cover, and this is the soft X-ray imaging telescope, which has a deployable cover. This is the CZT imager, and these are the scanning sky monitors, 3 number of them, which are mounted on a motor. They are driven by a motor in the 3 independent directions, okay, and they can monitor about half of the sky at any given time, and you generate power with this. Okay, so what will ASTROSAT do? Of course, ASTROSAT will look at the X-ray sky, UV sky, and study all kinds of galactic and extragalactic objects. But with LEX-PC and CZT, the prime targets will be the accreting X-ray binaries, which have neutron star, black hole or white dwarfs. Supernova remnants will be important for the study of both soft and the hard X-ray component, and AGNs will be of great interest from the viewpoint of studying UV and X-ray simultaneously and see how they are correlated. Then starburst galaxies, star forming region will be also of great interest for the UVIT instrument. So, ASTROSAT science goals will be that we will study, it will be a powerful mission for multi-wavelength studies because of the 5 co-aligned telescope, 2 UV and 3 X-ray instruments. AGN will be prime target. As you see, AGNs are very important because AGNs are, it is believed and all the observation suggest that AGNs are powered by massive black hole at the center, and AGNs have an accretion disk from which you get X-ray, UV and all kinds of radiation. Now, how the radiation in UV, optical, X-ray, they are correlated, from which, what are the sites of their origin, what are the processes which give birth to them, all these remain to be understood, and I think we can do, we will certainly improve in this by doing multivalent observation simultaneously. Right now, till today, only about a dozen AGNs have been observed, in a multivalent mode, for the simple reason that if you want to observe AGNs, you have to work out the logistics for pointing satellites which are in different orbits at the same target, and it has been a very difficult exercise. That is why you find that the results on the multivalent observation of AGNs are very limited. It will do correlative UV optical X-ray variation, measure time lags and do reversion mating, and construct energy distribution curve of AGNs over 5 decades in energy. Now, just to give idea to those who are not astronomer, that if you this is a galaxy known as NGC 4303 or M61. If you take optical image with Hubble, that is how it looks like. You see a spiral structure, you are seeing face on, and you see diffuse nebulosity, stars. But if you take ultraviolet image of this, you find that ultraviolet image, spirals are very well traced out. You see only bright hot stars, and then you will you see a bright nucleus even in UV. So UV, the accretion disk most likely is shining in UV. And then if you take X-ray image of Chandra, you see individual sources and a very bright nucleus. And if you further look deeper, you find that this nucleus is consistent with being a point source. Okay, so this is consistent with the scenario of the nucleus being powered by a black hole. This is just to show that if you do contemporaneous observation and not simultaneous observation, this is the kind of result you find. This is for 3C273 for in variety of bands at 5 gigahertz, 37 gigahertz, in millimeter region, in the infrared K band, visual band, 5 keV X-ray, and 20 to 70 keV. This is compiled from 23 years of data. Note that the data are not simultaneous, they are contemporaneous. That is why you can find that it is very difficult to make any sense out of it, very difficult to find correlation. When UV in X-ray, for example, you see factor 5 variation. We see in low energy also the same thing, but we do not see much change in the visual or in millimeter or in the K band. Okay? So these kind of observations people have tried over many years, and one could not learn much from them. Now, if you plot the spectral energy distribution from the previous observation, plot nu times f nu, which is arc centimeters per second the flux as a function of frequency, you will find that in the AGNs, this for 3C273, most of the energy lies in the hard X-ray and MEV band where the flux peaks, and that is why it is very important to do the study of AGNs in MEV region as well as in hard X-ray band, which will extend from about 15 keV to 100 keV here. Now, one of the results which was a promising result which was obtained in the early days was by having simultaneous observations ROSAT and IUE when IUE was working in early 90s, and you can see that in this very well known BLX source called S2155-304, which is one of the most rapidly variable BLX and very bright object, X-ray object, you see that there are correlated variations in UV, optical and X-ray. If you carefully look, you find that UV lags X-rays by about 2 hours or 3 hours, and this is consistent with the hypothesis that UV emission is produced by reprocessing of X-rays. X-rays are heat are incident in the part of the accretion disk, it gets heated up and radiates in UV. So this is consistent with the UV processing, UV X-ray processing by accretion disk and producing UV, but unfortunately recent do not give similar kind of results. So one is not sure that what exactly is the mechanism for UV emission. For example, here there is a very well known Seyfert galaxy called NGC 7469, in which you see that UV is leading X-ray. Okay, here you can, but at minimum UV and X-ray they are coincident. Okay, so it is very difficult to understand this result in the either by reprocessing model or by direct emission contribution from the accretion disk to the UV. So hopefully AstroSat will throw much more light on this. This is just another example of multivalent observation of a black hole X-ray binary. It was a transient discovered in 2006, 1817-330. It was followed by SWIFT, for about 120 days. So the SWIFT XRT and the optical monitor, one carried out the flux measurement over. Actually, unfortunately, the slide is gone below. It is 100 days here, 50, 100, 150. So you find that X-ray require a two-component model to fit the spectrum. There is a soft component and there is a hard component. If you take the total flux from the spectrum and plot it with the UV flux, you will find there is no correlation. Okay, Now, if you take only the soft disk component, which is temperature about the 0.5 keV or so, then again the correlation is poor. But if you plot the UV flux with the hard X-ray component, which goes from 0.5 and take it from 0.5 to 8 keV or 10 keV, you find the correlation is very good. So, UV tracks the hard X-ray component very well. So, that was for multivalent studies. Now, high resolution timing studies was one of the primary goals of the ASTROSAT mission. As you know, among all the wave bands, X-ray displays the largest amplitude of largest variations in the largest variation, and therefore, these variations are both periodic as well as sporadic and chaotic, and this will be studied with LEX-PC and CZT instrument in great detail. We will be monitoring the pulse periods, binary periods, the accreting binaries, accreting millisecond pulsars, anomalous X-ray pulsars. We will be studying the QPOs in soft and hard X-ray band in black holes and X-ray binaries, and high frequency QPOs studies which are very important because they can constrain the mass and spin of the black hole. Again, will be an important goal of ASTROSAT. Just to show, this is a artist image of a low mass X-ray binary system where you have companion, low mass companion from which overflows Roche lobe, and then the matter is attracted towards the neutron star in the binary, and it hits here, and there is a hot spot where the accreting matter first hits and it forms an accretion disk, and there is an accretion stream which can sometimes cause optical absorption, and then you have the disk wind. These X-rays emitted from the star, they shine on the companion star, the hemisphere facing it, and cause X-ray heating, and therefore it glows in optical, brightness increases. So, these kind of binary system will be primary targets: high mass X-ray binary, low mass X-ray binary, black hole binaries, and so on. Now, binaries have just to give an idea that binary stars in X-ray, they have periods, spin period ranging from millisecond to 1000 second, orbital period is range from 14 minutes to 100 days or even more. The QPOs you see from 0.1 hertz to 100 hertz, and you are flickering on all time scale as fast as 10 to 100 millisecond and longer period. Besides that, superposed on this is the precession of the disk or warping, due to which you see 35-day modulation, for example, in well-known source Hercules X1, whereas it is on for 25 days and off for the remaining period. Then in Cygnus X1, there is a 300-day periodicity, which is again attributed to precession of the disk. So, this example of sporadic variability of black hole, very well known black hole binary, GRS 1915 plus 10.5. We had a modest size instrument on one of the Indian satellite called IRS-P3, launched 15 years ago, which worked for 5 years. So, we studied this source very extensively during that period, and you can see that you see flares and random variability by more than a factor of 2 over time scale as short as 100 millisecond or even less. So, this is a characteristic of many of the black hole binaries. Now, the SSM, as I told you, will be used to monitor transients and the known variable sources. So, this is an example that how the SSS results will may look like. Your light curves of several binaries taken over a period of 500 days. So, you can see that the sources are normally dormant, many of the sources normally dormant, you do not detect them, they are below detection threshold. Suddenly they flare up, they last in that phase for 100 to 200 days, and then again become invisible, again we go to quiescent state. So, you have examples of neutron star and black holes. So, this kind of objects will be monitored. Now, the spin periods, the neutron star and binaries, accreting binaries, they have experienced accretion torque the angular momentum transferred by the accreting matter, due to which many of them spun up. But then there is an example of this GX1 plus 4, it was detected in early 70s. When it was detected, its spin period is 140 seconds. And look, in a matter of about 15 years, the spin period changed from 140 seconds to 110 seconds. It's incredibly fast. And then it went dormant, it was undetectable for quite a few years, suddenly came alive and then started spinning down. Okay. So, this kind of phenomena is quite common in X-ray binaries. This example of Vela X1, which also has episodes of spinning up and spinning down, and many other sources. So, AstroSat will be studying variability of spin period, orbital period, and so on. One of the very interesting class of sources which will be a prime target for AstroSat studies will be what are known as magnetars. Okay. Now, magnetars are the first magnetar was actually detected in the Einstein Observatory way back in 1980, and it was found from measurements, later measurements, that this has a very high rate of spinning down. Okay. Now, this was peculiar because if it was a single star, there is no evidence for any binary companion in this object, and of course, similar such 17 or 18 such objects have been detected so far. Now, if you take the p dot, which is factor of 1000 more higher or 10,000 higher than the normal radio pulsars, and take the period p and infer the magnetic field, you find that the magnetic field required is of the order 10 to 14 to 10 to 15 Gauss. So, all the red stars are magnetars, and it is a mystery how these magnetars are powered. Their luminosities typically range from 10 to 33 to 1036 arcs per second, and there is no binary companion. So, what is the source of power? So, one believes that magnetars are powered by magnetic field energy. One can give hand waving argument, say that magnetic field gets twisted, energy gets released, but what is the precise mechanism by which magnetic energy is converted to radiation is an unknown area. Now, these magnetars undergo spectacular outbursts many times, and when it happens, there is a soft gamma repeater 1900 plus 14, several times it has undergone spectacular outburst, and you can see that when it undergoes outburst, intensity shoots up by a factor of as large as 5 magnitude, and then you can detect the pulsations. Okay. And in general, magnetars are not radio emitters. In fact, I think only recently there are reports of 2 of them being found to be radio sources, but they pulsate. Okay. So, these are magnetars, essentially X-ray pulsars, which are single stars, single neutron stars. How they produce so much energy, why their spin down rates are high is something needs to be investigated. Now, detection of QPO is about 10, most of the QPO report, if you see in literature, are below 10 keV. There are hardly any observation of QPO above 10 keV, mainly because the detectors are small area, they don't have enough sensitivity. Because AstroSat will have LEX PC, which has large collecting area, it will have sensitivity to detect QPOs in all frequency range above 10 keV, and this will be a, I hope that this will produce probably few surprises. Now, do AGN show bimodal states? Do they also have QPOs? This is something which is again need to be explored. There are reports that intermediate mass black hole, 2 of them, one AM82, one IMBH, and one in the galaxy NGC4I4808, they show QPO. This example, you can see the result is only marginally important, 5 sigma, 6 sigma, but nothing more than that. So, one is to see whether this is QPO is genuine, and let me indicate that this QPO has been monitored in M82 from PC observation. What PC does, that every day or every alternate day it makes 1000 second observation of M82, and then you accumulate this data over long period and try to look for QPO. Now, remember that the QPO frequency goes in inversely as the mass of the black hole, and therefore, you expect this QPO frequency to be in the range of hours. Okay. However, there is now one convincing case for the detection of QPO in AGN. There is a Cepheid 1 galaxy called RG 10.34 plus 396, in which QPO with a period of 3733 seconds has been detected. This result has been reported in Nature about 2 years ago. And if you say that this QPO arises from the innermost stable orbit of the black hole, then you can put a limit on the mass, and this mass comes out to about 10 to 7 solar masses. So, AstroSat will have capability of observing QPOs from AGNs and variety of other sources. Finally, I will spend next 10 minutes on the spectral studies. As I indicated to you, AstroSat has 3 X-ray instruments which have capability to cover the energy band right from 0.3 keV to 100 keV. So, emission absorption features with medium energy resolution will be studied with the SXT in the 0.3 to 8 keV band, and cyclotron lines will be studied by CZT and LEXPC. Understand the complex multi-component energy spectra of galactic and extragalactic black holes sources. I will come to that. Measuring non-thermal spectral component in supernova remnants and accreting black hole binaries. This is example of the complexity of energy spectra of black hole sources. This is for Cygnus X1. You can see if you plot nu into F nu, that is flux in arc centimeter square second, is a function of energy. You see a big hump here, okay, and this is due to the power law component, due to Comptonization, and also the reflection component. And this particular source, most of the black hole sources display bimodal state. That means they have a soft state where the soft component is strong and hard component is weak, and then the hard state in which the hard components dominate and soft component is weak. And similar thing you can see even in the neutron star binaries, they display the same kind of spectra, but slightly, but you can see that the hard component is not very dominant. So, if you want to unfold the various components in the spectrum, you need to study simultaneously with a complement of instruments that cover the entire range. Now, for a long time people thought the supernova remnants produce X-rays mainly by shock heated gas which has temperature of 10 to 50 million degree, and therefore, most of the studies are below 10 keV with imaging instruments and non-imaging instruments, and one thought that this is all that supernova have. However, there are surprising discoveries from RXTE that supernovae, many of them have very non-thermal component in their spectra which extend right up to 100 keV, and this result was very tantalizing because this provides indirect. Now, if this non-thermal component arises from synchrotron emission which require electrons, typical supernova has magnetic field of 10 to minus 3, 10 to minus 4 Gauss. So, it requires electrons of 10 to 15, 10 to 16 eV to produce the synchrotron X-rays of up to 100 keV. Then it suggests that since electrons are there, protons must also be there, and therefore, supernova must be cosmic ray sources, as was postulated long ago and suggested by Ginzburg. Okay, there is a spectrum of microquasars GRS 19 plus 10 5. Conclusions are similar to Cygnus X1, not very different. Okay, but there is another interesting class of sources which are white dwarf pulsars. Actually, these intermediate polars are nothing but white dwarf analog of X-ray pulsars. They are in a binary system. The white dwarf is a magnetic field typically of few times 10 to 6 Gauss, and it produces X-ray pulsation, optical and UV pulsation. In fact, these sources will be very interesting to study both in UV and X-ray, because you can learn a lot about not only the emission processes, but also the interrelationship between UV and X-ray, whether the UV is coming directly as cyclotron emission from the pole of the star or is it reprocessed radiation. So, one surprisingly found that intermediate polars have again require 2 component spectrum, a soft component which requires a temperature of typically 1 keV, and a hard component which requires temperature of 20 keV, which is quite hard if you use a component model. And actually this study was done with the Suzaku satellite recently, and you find that the temperatures are much higher than what one expected. So, these kind of sources will again be very well suited for AstroSat studies. Now, magnetars, I told you about magnetars. For again magnetar, all early studies of magnetars were in soft X-ray band, But now recently Suzaku has carried out over the last 3 years very detailed study of about 10 magnetars, and they find that magnetars require a 2-component spectrum, one a black body component which is very soft, okay, typically about 0.5 to 1 kV, and a hard component which is quite hard, typical photon index is 0.4 to 1.7, okay. And you note that there is a gap here in the data, and the gap arises because Suzaku is a soft X-ray telescope and a modest area hard X-ray instrument, but it has it does not cover from about 10 kV to 15 kV or 18 kV, it is a gap. Okay. So, AstroSat will not have this problem, it will get continuous coverage over the entire band and it will provide better spectral measurements. Okay, finally, AGNs, AstroSat will also carry out detailed studies of the AGN spectra. As you know, the canonical model for the AGN, there is a massive black hole at the center, there is an accretion disk, and you have the soft for low energy X-rays coming from the accretion disk, which get componentized by the accretion disk corona, plasma in the accretion disk corona, and then some of them get reflected from the accretion disk. So, you get a soft component, black body component, which is given here. You get a power law component, and then you get reflection component. So, you see this Compton hub. So, this is how the typical spectrum of AGN will look like, and in fact, the spectra of many Seyfert galaxies measured with RXT confirm this picture broadly. Again, energy in the AGN you see a bump, blue bump due to the contribution from the accretion disk. You see this Compton reflection component here. So, this shows the energy distribution. Sorry, the energy distribution over the entire wavelength covering from radio to hard X-ray 10 to 5 eV, and we will be able to carry out more detailed studies of this kind of AGNs with AstroSat. Then AstroSat will, one of the prime target of AstroSat will be the study of cyclotron lines. Cyclotron lines provide a powerful method for studying the magnetic field of, you can directly measure the magnetic field of the neutron star by measuring cyclotron absorption features. Okay, and so far about 20 X-ray pulsars have shown to have cyclotron lines, and all the magnetic field measurements lie in a very narrow band 2 to 8 times 10 to 12 Gauss. Okay. Then high resolution UV imaging of all starburst galaxies, normal galaxies, AGNs, supernova elements will be done, deep UV surveys will be carried out. In fact, one is hoping that one will be able to go to 22nd magnitude in the UV band with by having deep exposure of 10 to 5 seconds or more. X-ray scans of galactic matter for detecting new transients. In fact, one of the great success story of RXT is that it repeatedly scales the galactic plane, and every time it finds new source. In fact, accreting millisecond pulsars have almost all been discovered from galactic plane surveys transient sources and found to be bright sources. X-ray monitoring of the sky for variable sources. So, one of the surprising results from 20 pulsars in which cyclotron lines have been detected is that cyclotron line energy changes with luminosity. Now, this is one thing one was not expecting. One was thinking that these lines are constant energy, but correlation with luminosity suggests that it depends on the accretion rate, and one can understand this by saying that when the accretion rate goes up, the region in the accretion column from which the cyclotron line in which the cyclotron originates moves up or down, okay, and therefore experiences different magnetic field, which is what we measure, and that is why this shifts. But I think more studies need to be done to verify whether this is correct hypothesis. Okay, AstroSat, I think this is the last slide, last button. AstroSat will measure the cyclotron lines much better than has been done in the previous mission. This is just a comparison to show you these 3 cyclotron lines have been detected from this very well known pulsar 4U115+63. In this pulsar, this is the RXT data, and you can see RXT data you barely can make out the absorption feature. You have to do modeling and do detailed fitting to make out that they are cyclotron lines. With WapoSex phosphate detector system, this is better, okay, you could see better thing. But then with AstroSat LEX-PC you can see that you will measure the cyclotron absorption features very clearly, order of magnitude better than done from the previous missions. So ASTROSAT will do a very exciting work on the study of cyclotron lines in the energy spectra of pulsars. Finally, UV imaging will be done, with this is the image of galaxy, which is 5 arc-second resolution. So, a 2 arc-second improved resolution of UVIT, you can see that you will be able to resolve all these, the nebulous regions and individual objects will be seen much better. So, morphological studies of galaxies you can do in a great detail in the UV band, probably for the first time. Okay. So, ASTROSAT pointing will have on a stabilized platform, which will be pointed in space to make it 1 arc-second capability, 3-axis stabilized well-proven satellite bus using 2 gyros, 2 star tracker, attitude controlled by reaction wheel system. So, life will not be limited by the by this mission life of at least 5 years. It will be a circular orbit of 600 kilometers to 650 kilometers, and orbit, one of the great advantages we will be able to put it in a very near equatorial orbit, and therefore, the background counting rates in the detector will be very stable, because when you orbit of 8 degree or less inclination, the cosmic flux is almost constant. It will be launched by a very well proven Indian polar satellite launch vehicle. So, conclusion, ASTROSAT will enable timing observation with 10 microsecond accuracy, broad spectral band in 3 to 8 keV for variety of objects, largest area hard X-ray detector, medium resolution capability of CZT for cyclotron line studies, SXT for imaging spectral studies, simultaneous observation with 3 coaligned X-ray instruments covering the wide spectral band, and often multi-frequency spectra covering visible UV, soft X and hard X-ray regions at the same time, UV studies and deep UV survey of selected regions, and detection monitoring of transient sources. So, in this talk I tried to give you a flavor of what kind of science is expected to come out of ASTROSAT. Thank you.
I probably missed it. How would ASTROSAT distinguish between spinning black holes and static ones?
Okay. See, as I said, there are several ways. One is that it will look for QPOs. Now, if QPO frequency, if QPOs high frequency are supposed to come from the innermost circular orbit around the black hole. Okay. I think it is supposed to be, for non-spinning black hole, it is supposed to be 6 times RG, and for spinning black holes, I think it is 0.3 or 0.6, I can't remember exactly. Okay. So, from and then for stellar mass black hole, for example, you know the mass independently. Okay. So, you can immediately find out that the innermost stable orbit size and whether it is consistent with that, and if not, that means it is a spinning black hole. Okay. So, that is one method. Another method has been developed by Ramesh Narayan and his co-workers, whereas the model the continuous spectra like they have learned for LMC-X1, and from that they can infer. So, these are 2 ways, and third is of course the asymmetric iron 55 line you see, which is a red word tail, and that tail tells you about the, from that you can do modeling and you can infer whether it is a static black hole or rotating black hole. So, there are 3 independent ways in which you can do it. Yeah, maybe you may have.
I will say a little bit about this in the topic.
Yeah.
Hello. I have a question and a comment. The question is just technical, but in the SXT, the soft X-ray telescope, what is the collecting area?
200 centimeter square at 1 keV, which will drop to about 25 centimeter square at 8 keV. As you know, the reflectivity drops sharply, and it is a modest area telescope, but the objective of using is that we can localize sources. We can also do imaging studies to a reasonable degree for kind of objects like supernovae, extended supernovae. You can do very good studies, and you can do spectral studies in selected regions and see whether how is the temperature distribution of the shock gas, for example, in supernovae. So, and the third objective is that the spectra turn over below 3 keV, and there is no way that with LEXPC you can do that, because LEXPC stops at 3 keV. So, by going up to 0.3 keV you can study the this absorption in sources, near sources or interstellar medium.
And the comment I had is just keeps coming up is this idea of measuring the mass of the black hole by the QPO frequency. That only will work if you don't have either outflow or comptonization that disturbs the inner disk. Because if you have that, you don't see the ISCO, you see another radius which might not be related, will not be related to the mass. So it's a worry that comes in the ultraluminous X-ray sources, for example.
Yeah, your comment is well taken.
What is the time scale at which this AstroSat will
Yeah,
be launched?
AstroSat instruments, all hardware has been fabricated. Engineering models have more or less been qualified. Flight models are in the process of being assembled. Some are already assembled, like LexPC, 3 LexPC units are already assembled. They will undergo now test, thermal test, vibration test, and then they will be calibrated finally, then handed over to ISRO, where the satellite bus is being built, and then ISRO will integrate with the satellite. And we are hoping that by the end of this year, it should be in orbit. That is the present plan.
Yeah,
Barring any unforeseen problem, we should be.
There was recently a couple of failures of the launches.
No, that is a different story. That is a GSLV, Geostationary Satellite Launch Vehicle. This is launched by PSLV. AstroSat weighs 1.6 ton, out of which instruments are 800 kg and satellite bus and subsystems are 800 kg. So it will be perfectly, PSLV is perfectly suited to place it in near Earth orbit. And PSLV has been successful consecutive in last 17 flights. So I think right now there is no worry on that score.
Okay.
One is, you made a very strong case about the advantages of having this multi-wavelength simultaneous observations and so on. So such a mission was a very natural one, and I was wondering why this was not done already. Is it because of some new technology or something, some advantage that we have here, or so that is the first question.
Okay. Answer to that would be, that normally when you fly astronomy missions, they are always dedicated to particular band, particular wavelength region. Hubble is for optical and also for near UV. There was actually UV photometer in Hubble in early days, and also the near infrared. Then Spitzer is just for infrared, because the thing is that if you want to put many instruments covering different bands, it becomes complex and difficult. When you are debating this mission and when you are working out the configuration instrument, we said we should have some strong point, okay, something which is unique about AstroSat, different from other missions. So why others have not done? Because it makes it expensive, complex and difficult. Okay, chance of failure also go up. So Chandra, as I said, and XM Newton, they are fabulous observatories. They have tremendous capabilities. Chandra's imaging capabilities unsurpassed and unlikely to be surpassed by any mission in future, because it's a complex instrument, took 15 years to make, cost $2 billion, and so all the missions have been dedicated to particular band, because that is the easiest way to do, and I think that is what one can concentrate.
And second question was about, poor theorists like us, like Sri, would like to sort of take a more distant view and say that yes, it is good to know about this, it's good to know more about this, it's good to know more about this. But are there some outstanding questions today about AGNs, for example, that one could not have answered unless one had simultaneous multi-wavelength observations? That one might be able to answer now.
Yeah. Okay, I told you, for example, that in the case of AGNs, we have this model, okay, that how the X-rays are produced, soft photons come from the inner region of the accretion disk, they get Comptonized and then reflected and go on, and UV emission comes from the cooler region of the accretion disk. Now, if you do right now, problem is that very few AGNs have been observed in simultaneous mode from different satellites, because it's a logistics problem to point at the same target given the different orbits and different logistics. So AGN studies, I think there is potential to learn new. Maybe are these models valid? So you will do reverberation mapping. You will study time legs of X-ray vis-a-vis UV or UV vis-a-vis X-ray to see whether really it is reprocessed radiation or directly coming. So lot of questions are there, and similarly high frequency QPOs, for example, this is an area which is largely unexplored. In fact, about 10 kV, I think there are reports of only 1 or 2 have detection of high frequency QPOs. For example, if AGN and stellar mass black hole are basically same kind of objects except difference in mass, then one should expect to see QPOs, okay, in AGNs scaled, QPO scale is 1 over mass, and that right now we have evidence for 1 QPO, which I gave example for one of these new Seyfert galaxies. But lastly, it's unexplored because you need long observation time for this. Because QPO, if you see fundamental frequency of QPO of 10 to 8, 10 to 9 solar mass, it will be around hours, okay, and half a day. And so therefore, even this is seeing is not the fundamental, probably first harmonic or second harmonic, okay. So study of QPOs that in AGNs, study of high frequency QPOs and hard X-rays. For example, hard X-ray, there are reports of 2 or 3 sources in which how do hard X-ray QPOs originate? If you take canonical model of black hole, the hard X-ray is supposed to be produced by Comptonization, okay, and so Comptonization of low energy seed photons. So now question is that how do you does it still preserve the periodicity which you see when it gets Compton scattered? Does it lose the coherence? These are questions that are open. So certainly it doesn't address any of the problem which Shri Kulkarni outlined yesterday. Is a different area. Yes, it will add more to the existing knowledge, but it has potential to generate new knowledge.